Hi, this is the return of the son of the main presenter. In this video, I'm going to be explaining how to build a high-power shortwave transmitter using switching MOSFETs rather than RF MOSFETs. And it's going to be a high-level modulation design, not low-level. So there's going to be no linear amplifiers. I might do another video on a linear amplifier, but those are very simple. You can find videos on that. They often use the BLF 188XR to do those things, and they're very simple. So this is a sort of different, more high-efficiency approach to building a shortwave transmitter, and also ham radio transmitter that operates within the HF band. So what I have here laid out on the table are the components that we're going to be using to build the thing. Starting out with this LCD controller screen. So this is the only part of the whole project that is going to be sort of black box. It's going to be just the module. I'm not going to explain it too much other than this is the device that you use to set the frequency, and it outputs a square wave with two outputs, not just one output. The one output has the square wave completely inverted compared to the other output. So it creates a push-pull where the square wave, one square wave is fully on and the other one is off. So it outputs a square wave that is about, I think, 5 volts. That output then goes into this amplifier deck. And this amplifier deck consists of, I have a board here that I can show you. Down here, there's the board laid out on the heatsink the way that I'm going to bolt it down. But right here you can see the general layout of the PCB. So down here I have the driver MOSFETs, which are TC4452s, and then up here I have the actual amplification FETs, which are Cree devices. Down there I also have a signal generator, and the signal generator can be used as a substitute for this screen. If you can't buy this screen, I'm going to include a link in the description to a store on eBay where you should be able to purchase this screen. But keep in mind, it is an amateur that builds these things. It might not always be available. So if you just need to generate the signal, you can use pretty much any signal generator that'll handle the frequencies in the HF range. You just need to have two different outputs, and you need to be able to lock the phases of those outputs so that you can generate essentially the same signal that this module would generate. So what I'm going to end up doing is we're going to move on to another part of the video downstairs where it shows me drilling all the holes in this block so that I can then begin mounting the components, and then you'll then see me beginning to place the components on the board on this table here. But before I get to that, there is something I should mention about legality. So if you want to use this thing legally, if you're in the United States, you need to have a ham license, unless you use this specific frequency, and I'm putting the frequency down below here. This specific frequency can be used if you remain within this calculation. Okay, so now I'm going to be heading downstairs to machine this heatsink. What I'm going to be doing is machining holes in the heatsink so that I can mount these MOSFETs in these little slots here. And then I'm going to be soldering all the components together under this camera here. Okay, so now I'm at the mill. This is the board I'm going to be milling right here. I measured out and marked each of the holes, and I'm going to set it down in the mill, and we're going to mill it. Yep, I'm gonna have to turn this around because this thing does not want to go back this far. Okay, we're gonna try a third way. Let me put it in sideways. There's another slot right down there, so I might be able to move this whole thing forward one. It's gonna be cantilevered a lot though then, so I don't know what its weight balance will be, but I'll find out. Okay, so I'm back. I'm gonna have to do a little bit of a compromise here because I can't quite get this thing to fit in here no matter what orientation I put it in. And I did try sliding this thing forward a bit. But even after doing that, I wasn't able to get it to line up so that I could drill all of these holes. So what I'm going to end up doing instead is I'm just going to mount 2 transistors on this side of the board and 2 transistors on the other side. So instead of using the full 8 transistors, I'm going to be using 4. Something I like to use while I'm milling is some canned air. It's really good to get the small burrs out of the holes. Another thing that I like to do with this stuff is if I'm hot gluing something, I can turn it upside down like this and it'll get the frost will come out. And if I'm hot gluing, I can instantly dry the hot glue. So it's an easy way to tack something down. Or even permanently for hot glue, it's very good to make it a quick glue. Alright, well, bust it off. Alright, I'm gonna have to try to get that out of there. Alright everyone, welcome back to the next part of the video. I just finished the milling right here. It took a long time because the drill bit busted off twice, and it was for 2 reasons actually. The one reason is because stupidly was drilling at a location where it was partway into one of these fins right here. And so it kind of pushed it sideways and snapped it off. And then the other reason is a little bit less obvious, but I put the thing in the clamp with this side against it, not this side. The problem is these kind of flex a little bit under a lot of pressure, and so it was slowly squeezing its way back out of the vise that it was in. So anyway, I got all of that sorted out now. So as you can see, I've mounted 4 transistors down here. These are Cree MOSFETs. This is the schematic that I'm using, by the way. I designed my board to incorporate extra MOSFETs right here, so I can use 8 if I want to. But on the schematic right here, I only have 4. But it's easy to make it into 8 because you use all the same components, you just duplicate it. So this is the schematic that I designed. Hopefully everything on here is correct. This is the first time I'm building this, so I don't know if it's actually going to work. But we're going to find out. You may also use other Cree MOSFETs. They're SiC MOSFETs. C2M 0280120, that's another one you can use, and I have 4 of them right here as well. One of them slightly more powerful than the other one, and also a bit more expensive. The one was about $5 a piece, and the other one's about $8, which is still really good for transistors that are going to be used for our RF application, because most RF MOSFETs cost like at least $50. And this thing might be able to go into the 1 kilowatt range, which a 1 kilowatt RF MOSFET is $180. That's like the BLF 188XR. So it's really cool to be able to use this type of design for an amplifier. I am going to set up these ferrite cores. So I got these 2 right here, and I got these 4 right here. So what I'm going to be doing with these is these are going to be glued together with silicone. I don't want to use hot glue just because it might melt. These might get kind of hot. Not super hot, but a little bit hot, enough to melt hot glue. So I'm not going to use that. But I'm just going to silicone these things together. They're going to be laid out like this. And they're going to be going on the output right here like this. And that is going to be the output balun. And then we're going to have, there's 2 solder locations right here, and then there's 2 solder locations back here. So we're going to be running a wire through this and a wire through the other side, and then this is where the output is. So we want 2 turns. So you can see right here it says mod plus. This is where the DC, modulated DC voltage comes in here. So right here, and then we've got this goes in between these 2 pads. We wrap the wire around here 12 turns. We do 12 turns of 14 gauge wire on here. And so connects there, and then the same thing on this side, like that. So I will be back in just a sec. I'm going to wind these up. So right here is the LCD display and control board. This is the board that generates the 2 square waves that we're going to be feeding into the input down here of this push-pull Class D amplifier. So this thing can be set from, I believe, 3.5 to 8 megahertz. You can see on the back it's got a DDS chip. It uses the analog devices AD9850. And you control the frequency using this rotary encoder right here. That is one of those clicky dials, and you can push it down to select. This is to drive the input of the amplifier. These drivers right here are the TC4452 from Microchip. So I've got 2 of these, 1 for each pair of MOSFETs right here. I have an extra space to put more of them as well, you can see. Right here's my schematic. Just to go over some of the components here lightly. I can do that right now, but if you want some more details, go to my website. It's dosaidsoft.com. dosaidsoft.com. There you'll find a full tutorial on this, documentation. It'll explain everything. But in the video, I'll just go over the basics of this. So this is a schematic of what we're building right here. You can see over here, we have our 2 square waves. That is what is generated by this board right here. They are then fed into the input of these drivers right here. So on this one I have 4 drivers depicted, but on here I'm only using 2 of the available 4 drivers. So here I just have 4 of them. Here I have the 2 voltage regulators that are here and here. I have not installed those yet, but they're going to be on either side here, and they're going to be sticking up from the board. So those are 8-volt voltage regulators. According to what I've read, 8 volts is the voltage that you want to use to drive these MOSFET drivers. Should be able to work with 12. I'm not exactly sure why they're using 8, but we'll find out. I mean, it is possible that using 12 might overdrive the final MOSFETs a little bit, or maybe it doesn't matter and they were just being weird. I don't know. These are the MOSFETs right here. These are the C2M 0160-120D. So right on the input of that, we've got a 3.3 ohm and a 10 kilo ohm. We have the same thing on all of those. Then on the output, we've got 100 pico right here on each of them. And then over here, we have our balun. This is our balun right here. That represents this. There's 4 of them like this. And those get glued together. So that's what this is right here. And then these 2 things, those are RF chokes that go here and here, made out of the T157.3s. And that's pretty much it. Then there's our output. So this is the schematic for the amplifier. But in addition to this, what else do we need? We need the driver that I showed you right here. We need this toroidal transformer. You want to use a 1-to-1 ratio toroidal transformer. This one is almost a 1-to-1. It's pretty hard to hold it under the camera here. This is a kilowatt, I think 100 or 1,000 VA, because it's got two 500 VAs in here. So it's one winding is 120 and the other winding is 100. So it's very close to being a 1-to-1, and it works pretty well. And it's plenty big for this application, so this is what we're using to modulate it. So what this is going to be like is we're going to have an audio amplifier going into one side, one set of wires here, and then on the other side, we have to figure out what each of the wires are. But then on the other side, we have the DC going through it and then going into this mod right here. This is our stereo. Well, it's actually not a stereo, but you can use a stereo if you have an old stereo left over from something. You can use a stereo. You want to use any type of audio amplifier. This thing's rated at 600 watts, but it's actually more like 300 watts because they rate it at like 2 ohms. So they try to get away with making it seem like there's a lot more power than there really is. So this is about a 300 watt mono audio amplifier right here. This is what I'm going to be feeding into that toroid to modulate this thing. The better way to modulate one of these would be to use PWM, which is pulse width modulation. That'll give you the most efficiency possible. But in this case, we're going to be modulating the old-fashioned way with, the audio transformer. The reason why I chose to do it this way is because it's still very close to being very efficient, in that this audio amplifier, I believe, is a Class D itself. So this is a very efficient audio amplifier. So the amount that we're going to gain by using a PWM is not going to be that much. And this is just a lot more, it's a lot simpler to, just use an audio amplifier with a toroid rather than trying to figure out how to design a PWM. Because the PWMs are not something you can just buy. You can't go out and buy a PWM. You kind of have to custom make one for this purpose. But this kind of thing, you can just buy any audio amplifier. You just need mono. You're not going to be using stereo. It's about 300 watts, and 300 watts can modulate 600 watts carrier. And that's carrier, not PEP. A lot of ham operators measure their power in PEP. I believe they do that just because it makes it sound like they have more power than they really have. But an actual AM broadcasting station measures their power in carrier power, not PEP power, which stands for peak envelope power, by the way. They measure it in carrier, and so this thing, being a 300 watt audio amplifier, should be able to modulate a 600 watt carrier signal. So that's a pretty large amount of power. That should be plenty sufficient for what we're doing here. So I'll see you again when I have glued these things together. This is non-enameled wire right here, by the way. Makes it a lot easier to solder onto, but it means that I have to make sure that none of these have bridged in here. So I have to make sure there's a gap in between each of these windings. Okay, something I wanted to mention about installing these transistors here. So I finished getting this thing properly installed. I put the number of windings on the opposite side, so I had to reverse it. But it's 1 on this side and 2 on the outside. So this is all soldered down, and it's pretty secure even without gluing it. Down here with these transistors, right here you can see that the central pin is the output pin on these transistors. I don't know why they did it that way. It seems like a stupid way of doing it, actually, rather than having one of the side pins being the output. Having the central one as the output is a little bit limiting, but that's what they decided to do. So what I had to do here is, you can see the central pin goes to a trace that goes underneath this pin and then goes up to this bus right here. So all of these combine together and go up to this bus, and then on this side they combine and go to this bus. So what I ended up doing here is, just to be safe, because this central pin is the output and it has a trace that's passing right under the ground here, which is this pin. When I bent this pin down, what I did was you jam a piece of metal in here. I jammed just this tweezers in here and bent it down on top of that, just so that this thing is not laying flat right on top of this live. I put some pads underneath each of these. So these smaller drivers just have a silicone pad under them with no thermal grease. These, you can even see the thermal grease leaking out here. These have thermal grease, Arctic Silver thermal grease. And they also have mica pads underneath them. Just because the back of these transistors are connected to the output or the drain, and so we want to make sure that that's not contacting with the heatsink, because the heatsink is the ground. I got the components set up here on this piece of paper. I've labeled each one of them and grouped them together so it'll be easier to put it on the board. I also chopped off the ends of them to make them shorter. You can see this is where I've gotten so far. Looks pretty good to me. I like how it looks. It looks very professional, very symmetrical. Silicone pads on these things just to make sure that they spread the heat a little bit better. I got a cat coming under here right now. No, Katie. Hold on. There's one discrepancy, however. With these 4 100 picofarad capacitors, I'm only using 2 of them because I think it probably won't need quite as much. These are the capacitors that go here on the output. There's a total of 4 of them. They're 100 picofarad. These are the things that are most likely to need to be changed and tweaked with this design. Hopefully everything should work just as is, but if it doesn't, these might need to be tweaked. I bought several different values. I bought some 47s, some 100s, which I have here, some 270s, and I think some 470s. Just to experiment with changing these to see what happens. It may even work without them entirely, but we're going to start out with just 100 picofarad, one on either side. Okay, so I finished. You can see it here completed. All the components on there. And these, I skipped these because I'm not adding as much capacitance. Same with that one. I might change that if it doesn't work, or to see if it works a little bit better with different values there. But now it's just time to hook up the input and hook up the RF output connector. And right here, this is the output low-pass filter. You need to use a low-pass filter on this because it's a Class D amplifier. It'll produce a lot of harmonics if you don't. So this is our harmonic output filter. So right here, I've got some RG402, I think, So we got this coax right here, really nice and easy to solder to because it's got a metal sleeve here. I didn't have to strip this at all, it came like this. So then this hooks up to where it says RF on my amplifier, just like this. And then the output goes through the filter and comes out this end connector right here, and it has a little bulkhead, so if I ever decide to mount this in a case, I can do that. So that's pretty much it. I'm going to do those two things, and then I'm going to power up and I'm going to test it. However, you're going to have to wait for part 2. Don't worry though, it's not going to be very long before I post that because there's not really much of anything to do. But I'm going to do that in part 2 just in case something goes completely wrong, because I have no idea what's going to happen. I really haven't tried anything like this before. So it should work, but just in case it doesn't, I'm going to be, doing it a little bit of work off camera to make sure that I have everything absolutely precise and perfect. I don't want to have to think about having the camera in the background and maybe not paying as much attention to certain things as I normally would. There's a link in the description where I post all the schematics on my site. I post an archive containing the PCB files, and a little bit more in-depth description of exactly what I'm doing here is found on my website. So if you want to follow this sort of project in a text-based form that's easier to follow, I recommend going to my site and checking that out. And also, I have a link to donate via PayPal on my site. I'd really appreciate it if you guys could do that. It helps me build these kind of projects. There's a little link on the side of my site that says donate to the son of the main presenter. Just click there. It's a one-time payment, so you don't have to worry about it. It's not like Patreon where they keep charging you. You just put in whatever you want and it'll be a one-time payment. It'll help me do some more expensive projects in the future, like the Hack RF or the Lime SDR is something that I'm thinking about doing. Thanks for watching, guys. Really appreciate the support if you can, and stay tuned.